Welcome all to Physics for All. I'm Shilpy Bhullar and we are doing video lecture series on the topic vector analysis. And as promised, today we are going to discuss surface integral and volume integral. We have already done line integral. Since we have only three integrals that we deal with in physics as we live in three-dimensional world, so we have line integral, surface integral and volume integral. So today we are going to discuss surface integral and volume integral. As you can see in the figure, these orange colored arrows, they denote a vector field. So suppose we have this vector field A which is present here, and A is depending on x, y and z variables. So obviously whenever there will be change in x, y and z, there will be change in vector field A, and you can see that these arrows are just spread over this entire region. Now in line integral, we used to consider some path or loop or a wire or just a track in a vector field. But here in surface integral and volume integral, as the name suggests, we have a vector field, but for surface integral, we are going to consider a surface within that vector field. And for volume integral, we would consider some volume. So here this yellow colored region, this denotes surface. Okay, so this is surface X that we have chosen and within this vector field. So A vector field is spread over this entire region shown by orange colored arrows, and to solve, to get some value, we have considered this yellow colored surface S within that region. So now everywhere we are going to feel the effect of vector field A because it is spread over the entire region. But still we want to find the value of vector field A over this entire surface. We know that the field is spread over the entire region, but we are concerned only with this particular surface. We want to find the value over this surface. So for that, we will find surface integral. So let's discuss surface integral first. As you can see, we have drawn this vector A here, and then a normal would also be there. Since now we are not dealing with curves anymore, we are dealing with surface, so we have to draw normal, and normal is always drawn perpendicular to the surface. So this n cap is a positive normal of unit length. Now since surface S is the region that we are interested in, but to solve, to find the value of vector field A over this region, we have to consider some small surface element. So here we have considered this ds as the small surface element. So it has basically area ds. So whenever we used to talk of line integral, we used to consider line element. We used to consider dr, which was just the change in position vector. But if we are considering surface integral, we are considering a surface, then the element chosen should also be a surface. So always remember, if you are dealing with line, curve, the element chosen will be a line. See, we cannot have an area on a line. It is not possible. It's meaningless. If we are considering a surface, then the small element that we consider for integration, that has to be surface. And if we are considering a volume within a specific region, then the small element that we would pick for our integration has to be a volume element. Since now we are dealing with surface integral, so for surface S, we have considered this small surface element ds, which we call it that it has area ds. And now the n cap, this unit vector has to be drawn, and it is drawn normal to this element. If we have any open surface, like open surface is what? It's a line, it's a curve. Then this normal is always drawn in the same direction as that of vector. As we did before, you can see here in this particular figure that we discussed for conservative field, this your vector field A is pointing in this direction, okay, but the normal that we have chosen, it's always in the same direction. So this is the small element dr that we have chosen. Okay, this is dr because here when we were considering just the curve c1, so c1 is a curve, it's a line basically, so we have to consider some line element. So in case of line integral, the normal is also in the direction of the vector field if you have an open surface. But if you have a closed surface, that means you have exactly a surface, then the normal would always be perpendicular to that surface. So whatever surface element we consider, normal has to be drawn perpendicular to that surface and outwards from that enclosed surface. So that's why this n cap is pointing outwards from this ds. And let theta be the angle between this n cap and vector A. Now n cap and vector A are no longer pointing in the same direction because that only happens if you have curves, if you have open surfaces. The other term for curves, tracks, lines is open surface, something which is not closed, so you cannot consider it to be a surface basically or an area. But if you have surface, then the n cap would be pointing always in perpendicular direction and vector A could be anywhere. So this theta is the angle between them, and this component ds is perpendicular to A. For one particular case, here we say that this n cap is perpendicular to ds. So if we want to find the component of A which is perpendicular to ds, because we cannot act in any direction, the most comfortable direction is the perpendicular direction because we have some formula that we can use. So here A is pointing in all directions, but we know that n cap is perpendicular to ds. Now we want to find the component of vector field A which is perpendicular to ds. That is possible because A is pointing in all directions. So we can pick that particular component which is perpendicular to ds. That is given by A dot n cap. Since we want to find component of A which is perpendicular to ds, but we know that n cap is perpendicular to ds. So that means we have to take dot product of A with n cap. Because A might be acting in some particular directions, it is acting in all directions. You can see the arrows are pointing in all directions. We only want to find the component of A which is in perpendicular direction to ds. And that is also possible only because of n cap, because we have n cap. Otherwise, it won't have been possible for us to find this component, perpendicular component. So here we have to take dot product of A with n cap. And again, we are interested in dot product only because we want to find the value, some numerical value, some result. Since n cap is a unit vector, so its magnitude would be 1, and theta is the angle between vector A and n cap. So the answer would be A, which is the magnitude of vector A, into 1 into cos theta. So it's simply A cos theta. Flux of A through element ds is A dot n cap ds. Say we have written here element ds with vector because n cap is associated with ds. This, if you want to write, you can mention this particular region without arrow. So let me do that. Okay, now this is our region ds. You can see this is ds, simply a magnitude. When n cap gets associated with it, then this combined entity becomes this ds vector, because you are actually multiplying a vector with some magnitude, so you will get a vector quantity. Now flux is what? Number of field lines passing through unit area. So we have considered surface, which is basically an area. So the amount of vector field lines passing through this element ds now, because we are considered with this n cap also, that would be a dot n cap ds. So either you write ds vector or you write n cap ds, that is the same thing. So I can mention it here. This is basically a dot ds. Okay, ds elements consist of n cap and ds. Here in the figure we considered only element ds, and then of course the normal has to be drawn, and when normal is taken along with ds, then we get this surface element ds with an arrow overhead. Now we know how much flux is passing through the small element ds that we have considered. So now we have to take the integral because we have to find the value over this entire surface, which is colored in yellow. We only know the value of a through ds, but we want to find the value of a through this entire surface, over this entire surface. So we have to integrate. The integral that we will take over the entire surface, that is called normal surface integral, okay, or simply surface integral. So the total outward flux of the vector field from the surface S. Now here we are talking of the surface S. So that would be A dot ds that we have to take, and then we have to integrate it over the entire surface, and that's why I have written this S. This indicates that the overall area. Here we don't have any limits. We have limits only in case of line integrals, because a line or a curve actually starts from some point and ends at some other point. So we know what is the lower limit and upper limit. But this surface is an area which is spread over this region, and you can see it's being curved also. It's very difficult to say what would be the lower limit or what would be the upper limit, because it is possible that it is spread over just a particular region where the value of a particular coordinate would be same throughout. In that case, we have to divide that particular region into sections, which we would learn while we will try to solve the numericals. But here, just to show that we will use double integral. See, single integral corresponds to line when you have just one coordinate involved. Double integral is for the surface when you have two dimensions, when you are talking of two dimensions. See, surface or area includes two dimensions. And if we have volume, which includes all the three dimensions, then we have to use the triple integral. Here, as we are talking of area, which represent two dimensions, that means two coordinates would be there, would be involved. We have to write down two integral, and then we have to mention the surface also. Which surface are we talking of? And sometimes if we are having closed surfaces, because surfaces are usually closed, we also represent it with this circle, as we did it when we were discussing line integral over closed loops. So anything which is closed, we often denote it by this circle. Now for this, what we can do is, we know what is A dot ds, that is A dot n cap ds, and we have also done what is A dot n cap. This tells us that A dot n cap is simply A cos theta. So we can put it here, and this gives us A cos theta ds. So always take care of the dot, because this A dot n cap actually gives us A cos theta. And then no more dots, because here you have already taken the dot product. So this is the answer. So either way, like if we have any surface then we have to solve it like this. This would be the final answer. And then we have to take the double integral with respect to two coordinates whatsoever are involved. The other way to write it as is that you know that vector A is axi cap plus ayj cap plus az k cap. The way we used to represent vector r or dr vector, you know dr vector is dxi cap plus dyj cap plus dzk cap. Similarly, we can mention this ds vector also, this ds vector. We can write it as ds x I cap plus ds y j cap plus ds z k cap. It's just the way to represent, because we have to show the x component, y component and z component, but it is an area element, so we have to write ds with x as subscript and here y as subscript and then z as subscript. We know both the vectors and we have to take the dot product as shown here. So this thing can also be written as a dot ds. We have to take dot product of both the vectors. We obtain this. As you know, in dot product, I cap only interacts with I cap and the same with j and k caps. Now I'm going to write the direct answer. This is the final answer. Thus, we can represent that our surface integral a dot n cap ds is also equals to ax dsx plus ay dsy plus az dsz. Whatever is applicable, that formula we pick. If we have all the components available to us, then we try to solve it like this. If we have angles involved, then we try to solve it like this. So both are just the representation of a dot n cap ds or simply a dot ds. The thing is, we are always concerned with dot product, and if you are talking of area which is two-dimensional, we have to use double integrals. So this is surface integral. Now let's discuss volume integral. As you can see here, a xyz is the same vector field spread over the region. We considered this surface S, but we have also considered some volume V. You can see now it's a three-dimensional volume that we have considered, and we want to find the value over this volume V. Again, we have to consider some small volume element because it's not possible to find the value over the entire volume in one go. Thus, we have to consider some small volume element and then we'll integrate over the entire volume. Here, there is closed surface which is enclosing volume V. Surface can be open surface as well, as here we were talking of this open surface S, but if some surface encloses a volume, so here we have this volume V. That is some other surface which is closed, which is closing, and thus if surface closes, it definitely encloses some volume. Now you know how we did line integral, how we found surface integral. Can you judge how can we write this volume integral? Ultimately, the answer is going to be same. We want to find the value of A over this particular volume V that we have chosen. Well, you know that it will be vector A, and then since now we are considering volume element, so instead of ds, there would be dv. Now for ds, you know that we have written ds with this arrow overhead. That means it is ds vector. And that was because this n cap came into picture. We considered simply some surface ds which definitely had some numerical value. But since this n cap is always there whenever we consider some open surface, so there is some vector which is a unit vector which always points in the direction normal to the surface. So due to this n cap, this ds got that vector feeling. But in case of dv, this dv includes what? It includes all the three directions. This dv is, this is how our dv looks. It is a volume element, very small volume element, and volume includes all the three directions x, y, and z. So this dv is basically small change in x, small change in y, and small change in z. So dx, dy, dz. All the three directions are involved. Can we include any particular n cap here? No, it is not possible. N cap is possible for some surface because surface is two-dimensional, and then we account for some unit vector which is pointing in basically direction perpendicular. So that perpendicular gives us the feeling of three dimension. That third dimension is basically the direction of unit vector, like we did here. Direction of unit vector n cap. See, ds is spread over the region. You can say the region is xy. It is spread over xy plane. But this n cap actually gave us the feeling of the third dimension, which is the height, which is the z axis. But in case of volume element dv, we are already considering all the three directions. So pointing some extra vector is meaningless. We cannot show any vector like n cap which is pointing in some particular direction, because either we can make n cap in x direction, or we can make it in y direction, or we can make it in z direction. But we already have dx, dy, and dz with us. Like here, we already have them, and we cannot have, and we don't have fourth dimension in space coordinates. In space coordinates, we only have x, y, and z, length, breadth, and height. That's it. We cannot have some fourth extra positional dimension. So here there is no role of n cap. I hope you have understand this thing. You have understood this thing, that n cap has no meaning here, because it is always used for some dimension, for some direction which is not there before. In line, we make use of dr vectors, and we know in case of line integral, the vector n cap is in the same direction as that of vector a, because we need not to find any surface or volume. We are only concerned with one direction, and solving one direction is very easy because we have to solve just one integral. But when we have a surface which already incorporates two dimension, then it becomes necessary that we make use of that third vector, which would give us the idea of third dimension, which is always the n cap. But in case of volume integral, when we are already considering some volume element which includes all the three directions, we don't need n cap. So there is no need of n cap. N cap is what? It is a directional vector having unit magnitude. But we already have all the three directions involved in dv, dx, dy, and dz. So we don't need n cap. Now, since there is no n cap in this expression of dv, what does it look like? Does it look like a scalar or a vector? Well, yes, it is a scalar, since there is no vector involved. You cannot see any vector. There is no del operator. There is no n cap. We know del operator x like vector. We know n cap x like vector. But nothing is here. We only have dx, which means small numerical change in x, dy, which is small numerical change in y, and same is for dz. So this dv is a numerical quantity, a scalar. And in all the line integral and surface integral we did, we were finding dot product of vector A, because we are concerned with the value of this vector A over this region. But here we have vector A and scalar dv. In earlier cases, we had vector A and vector dr for line integral. We had vector A and vector ds for surface integral. But here for volume integral, we have vector A, but we do not have vector dv. We have a scalar dv. So can we take dot product here? No, we cannot take dot product because dot product is always found between two vectors. So what we will do here? Let's see. Now let's write down here. This is vector A and this is dv. Since we have one vector and one scalar, we cannot use dot product. We can also not use cross product because both products are taken between two vectors. So we will simply write down these two, and then since it's a volume element, it includes all the three directions. So we need triple integral for that. Okay, so this is the way we're gonna use it. So this is simply a multiplication of vector A with dv. And then we know that this is basically vector A, which can be written as ax I cap plus ay j cap plus az k cap. And then we have this dv, which is dx, dy, dz. Alright. And then how can we write it? This becomes, now you know that our final answer would be having I cap, j cap and k cap. They are not removing, they are not going anywhere. They are still here and they will remain as such. So that means the answer obtained is a vector. Okay, and then we can split it because this would mean that ax multiplied by dx dy dz because I cap is here, then ay multiplied by dx dy dz because j cap is here, because all three terms that we would obtain, they would be pointing in all the three directions. So these are three different terms. So we can split it as I cap triple integral ax dx dy dz. And since this was volume element, so ax would be having some components of x, y and z. It is possible. But most of the majority of the components would be from x. Okay, that's the thing. Or sometime it is possible that it would be, this would be simply x, but the result would give us x, y and z, because you know, if you have nothing here and just dy, answer would be y. If you have nothing except x and there is dz, you would get z in the answer as well. So suppose we have this ax as x square, and then you are taking this dx, dy and dz. How would you do that? This would be, first you will try to solve it like this, and this would give you x cube by 3. Okay, now this is being used, but dy and dz are still waiting. So dy and dz, and then you would write down double integral because you have already used one integral. We would solve them by using some examples, we would definitely, but I am just giving the hint. Then again, what you would do, you would apply dy here now. You would apply dy. Since there is no y term, so this would simply give you x cube y by 3. And then dz is left. And now only single integral because only one coordinate is left now. And again you can see now this dz would apply here since there is no z term. So the final answer would be x cube yz by 3. So in the answer you would obtain all the three components since it is volume integration and all the three directions would be involved. So we can continue writing it as plus j cap ay dx dy dz and then plus k cap triple integral az dx dy dz. So this is the final answer. This is the answer that we obtain by taking volume integration. And I cap, j cap and k cap will still be there. They all will be pointing in the direction. So the answer obtained would be a vector. So this was all about surface integration and volume integration. So we discussed both surface integral and volume integral here. We have already done line integral. So this is all about the three integrals that we discuss in physics. Now in the next video, we'll continue with the divergence of a vector function, because in the previous videos we only discussed divergence mathematically, but now we are going to discuss its physical significance, and then we will use it in very important theorem. So thank you all for joining me today.